A new way of removing carbon dioxide from a stream of air could provide a significant tool in the battle against climate change. The new system can work on the gas at virtually any concentration level, even down to the roughly 400 parts per million currently found in the atmosphere. Most methods of removing carbon dioxide from a stream of gas require higher concentrations, such as those found in the flue emissions from fossil fuel based power plants. A few variations have been developed that can work with the low concentrations found in air. But the new method is significantly less energy intensive and expensive. The technique based on passing air through a stack of charged electrochemical plates is described in a new paper in the journal Energy and Environmental Science by the MIT researchers. The device is essentially a large specialized battery that absorbs carbon dioxide from the air or other gas stream passing over its electrodes as it is being charged up, and then releases the gas as it is being discharged. In operation, the device would simply alternate between charging and discharging, with fresh air or feed gas being blown through the system during the charging cycle, and then the pure concentrated carbon dioxide being blown out during the discharging. As the battery charges, an electrochemical reaction takes place at the surface of each of a stack of electrodes. These are coated with a compound called polyanthraquinone, which is composited with carbon nanotubes. The electrodes have a natural affinity for carbon dioxide and readily react with its molecules in the air stream or feed gas even when it is present at very low concentrations. The reverse reaction takes place when the battery is discharged, during which the device can provide part of the power needed for the whole system, and in the process ejects a stream of pure carbon dioxide. The whole system operates at room temperature and normal air pressure. The greatest advantage of this technology over most other carbon capture or carbon absorbing technologies is the binary nature of the absorbent's affinity to carbon dioxide. In other words, the electrode material by its nature has either a high affinity or no affinity whatsoever, depending on the battery's state of charging or discharging. Other reactions used for carbon capture require intermediate chemical processing steps or the input of significant energy such as heat or pressure differences. This binary affinity allows capture of carbon dioxide from any concentration, including 400 parts per million, and allows its release into any carrier stream, including 100% CO2. That is, as any gas flows through the stack of these flat electrochemical cells during the release step, the captured carbon dioxide will be carried along with it. For example, if the desired end product is pure carbon dioxide to be used in the carbonation of beverages, then a stream of pure gas can be blown through the plates. The captured gas is then released from the plates and joins the stream. In some soft drink bottling plants, fossil fuel is burned to generate the carbon dioxide needed to give the drinks their fizz. Similarly, some farmers burn natural gas to produce carbon dioxide to feed their plants in greenhouses. The new system could eliminate that need for fossil fuels in these applications and in the process actually be taking the greenhouse gas right out of the air. Alternatively, the pure carbon dioxide stream could be compressed and injected underground for long-term disposal or even made into fuel through a series of chemical and electrochemical processes. The researchers have set up a company called Verdox to commercialize the process and hope to develop a pilot scale plant within the next few years.